That is that. We are back. Today is May 1st, and May is Electrical Safety Month. So we're kicking off Electrical Safety Month talking about incident energy and the code requirements NEC 2020, and I'm also going to share some best practices as well. So it's Happy Electrical Safety Month. Thank you for joining me in this session. We're going to have 2 hours on arc flash. We're going to talk about arc flash calculations. We may get a little bit more technical at some points, and then we'll roll it on back. But I don't have my slides associated with letting you know that those of you who are on WebEx are on mute. Please leverage the chat. I'm going to have that up there. We have I have the chat going. I have that. I have those who are on YouTube. Please, if you're on YouTube, you're already familiar, and thank you for tuning in on YouTube. And I know you guys will help each other keep the dialogue going. If you have questions, pop them in there. I'm going to periodically be looking up there, and yes, Mr. Froming, I will specify Eastern time zone. Sorry about that. We got Murfreesboro. We got Costa Rica again. Man, we've got everybody. It's really awesome to see how many different people are dialing in via YouTube and in WebEx. All right, so everybody is on mute, and I must say that again, I'm Thomas Dimitrovich, as you all know. I am on various code making panels. I get involved with standards. I am speaking on my behalf, not NFPA's, anybody else's. The information I provide is my opinion and my opinion only, and I'm entitled to that, just like y'all are. So please, if you have a difference of opinion, put it out there in the chat box. Let us know. And bring up any of those items where you may disagree with something that I said. We're here to learn from each other. We have a lot of smart people on the line, and I love to hear from all of you. All right, so let's start this by looking at the quiz results. Something went wrong with Mentimeter, so let's try it again. I'm going to just bring up my Mentimeter went south on me. I'm going to give you the next slide here because a lot of what I'm going to be talking about, it revolves around a few key areas in the National Electrical Code. Spaces about electrical equipment. Some of these are going to be direct, and some will have an indirect relationship to our discussion. And I say direct versus indirect because 110.16, obviously, if we're talking arc flash requirements or arc flash calculations, 110.16 is titled arc flash hazard warning. So that's a give me, right? 240.67 and 240.87, arguably, and I say arguably, this is a good discussion point because I say arguably those are the first time. What I used to say were the 240.87 and 240.80, actually 240.87 was the first requirement in the NEC to address arc flash reduction. And I was wrong. Someone pointed that out to me in a class, and they did it really nicely. They pulled me on the side and they said, Mr. Dimitrovich, I appreciate your class and blah, blah, blah. And then he says, I disagree when you say that the first requirement in the National Electrical Code that addressed arc flash reduction is 240.87. It's not a historical moment as you had professed. And I thought that was interesting, and I was very intrigued. And he explained ground fault protection of equipment was the first arc reduction technology that was put into the code, and that entered the code back in 1970. So I thought that was interesting, and I did my research. When I get challenged like that, I like you should be questioning what I'm saying, and I will question what you say. I'll do my own homework, and I did a lot of homework on ground fault protection of equipment, and I did learn that GFPE did go into the National Electrical Code in 1970, and it was the first technology. You got to remember what was going on in the early like 50s, 60s, and 70s. We were going from ungrounded systems. Remember, early in our electrical history, we had ungrounded systems, delta systems. Why did we do delta system? Well, that first ground faults that give me, right? We had this discussion. I brought this up a little bit a couple days ago. That the ungrounded system was all your motors and everything were delta configurations. They didn't need that grounded conductor in the system because electricity was initially used for your industrial applications, for rotating motors and things like that. Well, the problem with an ungrounded system are those transient voltages, right? So I have one, and they could be caused by many things. I could have had a ground fault. I could have had some sort of electrical disruption that would cause severe overvoltages, and it would damage motor windings and all this other good stuff. And then I think probably what happened somewhere, down the road, there was an engineer who said, you know what, I'm going to ground one of the corners of this system because I've done my math. And I think we can live with a corner grounded system. And they grounded one of the corners of that delta system, and they realized, crap, I not only don't I have those severe voltage fluctuations, but I can provide a lower voltage leg off of this. Maybe I center tap or whatnot. Well, they shifted the issue though. So here's what happened. Back in the day, they went from ungrounded to grounded. So when they grounded the system, the fault currents went up. They had higher fault currents. I say that they had fault currents, and we could have a debate on whether or not one of my arguments is, one of my discussion points is that your first fault in an ungrounded system is free, right? That second one's a doozy. So when they grounded the system, they eliminated that first ground fault, and that first one now is the doozy. So you had the more likelihood or the chances of you can't live with one ground fault in the system. So that's the first thing that happened. So they went from ungrounded to grounded. Then they went from an average of 208 volts on the services to 480 volts. And what does that do? That's like turning up the pressure, baby. If I relate that to water. That's like you got a bigger dam, right? Because now you've got this voltage is pressure in the power distribution system. So you grounded it. You don't have that give me first fault. You increase the voltage, and then we went from an average of a 600 amp service to a 4,000 amp service. And what that did was move the instantaneous further to the right, and we're going to talk about what that does to us. And you have added delays because back in that day, they didn't have electronic trip units. You had these big thermal mag breakers. I call them, they had the big beer gut, right? Well, if you look at that trip curve, that big in the thermal side of that overload region, it had that real big error band, and that caused a lot of incident energy. And what we experienced in the 50s and 60s were a lot of events at service entrance equipment where you had catastrophic failure. I would call them arc flash events, and that equipment looked like what we call today an arc flash event. So, and you think in the late 60s, in the 60s, just think about computers. Computers were going from rooms to almost a desktop. I'm not sure what year the first desktop became available, but I know that we went from having a room full of computers to something that maybe operated on a desk, so to speak. So electronics was going and progressing, and we were able to put electronics inside of relay type enclosures. And then we were able to take that and make it even smaller and get it into these big power breakers. And we were able to provide ground fault protection of equipment. And if you look at the dialogue, look at the panel, the public inputs, in the 70 code and the year prior, there was a lot of discussion and debate about service entrance equipment, burn downs they called them, and they had pictures of arc flash events. IEEE had a lot of papers in that time period of these arc flash events. This was even before Ralph Lee's paper that we got into arc flash. So we had all of this going on, and then we had Westinghouse, and you had GE and a few others. I think Westinghouse was the first one to come out with the ground fault protection of equipment in their breakers, and that just basically opened the doors up. And then you had requirements now in the code for that equipment at service entrance, and really it hasn't changed since 1970 all that much. So that was his point. He was 100% accurate. Although at the time I was like thinking, well, you know, this guy's probably smoking a little weed here, but he was right. He was absolutely right. So in any case, let's take a look at the quiz. All right, I'm glad I got that, and I was able to get my quiz working. And I'm seeing there's some dialogue. I had research when GFPE was introduced for a hospital. It was built in 1970. The owner wanted to know if it was originally built to code. Those old books are hard to find, and NFPA wants a pretty good fee to view old code books online. Yeah, you know, and I'll tell you what I benefited from. I got it in my library right here. This is 1968 preprint. This is the 1968 preprint. This is the 1971 preprint. And what's really cool is back in the day, they did everything via paper. So they take these documents and they have the public inputs, or I don't know what they called them back in the day, but they had the panel statements. They had the explanation of the vote, they called it. They had the submitter and the supporting comments and whatnot. So all of that input is right here. So I was able to dig that stuff up, and I did purchase earlier versions of the book. And I'm just looking to see if 230.95. I think it was even 230.96 was working space. 230.95. It was even 230.95 back in the day. That's why our industry hates change, right? And it talked about ground fault protection of equipment. It's recognized. So that's the fine print note. There was the negative votes. I've opposed only to the parts of this proposal, namely the time current values of 1 second at faults. So this, gentlemen, and this is the other thing. Ground fault protection of equipment is there for arc reduction, but what's our clearing time that we permit in National Electrical Code? 1 second clearing time. And what we're going to learn today is that 1 second is a heck of a long time for incident energy. So this gentleman, Jutstrom, Jutstrom, said that they didn't like that 1 second clearing time. And then there were some affirmative comments as well. And Stanbeck is on there. So that was the submitter of this was NEMA, actually, for this, and it talked about the issue. So in any case, it's hard to find these preprints, but when you get them, they're gold. All right, so let's talk quiz. What was the first question? Incident energy at service entrance equipment is determined by the clearing time of the service main overcurrent device. And where's my data? There it is. Woo, took time. Whoa, you guys are split on this one. Incident energy at service entrance equipment is determined by the clearing time of the service main overcurrent protected device. I got 30. This is cool. 36 and 37, and then three honest people. There, three honest people in the room. That's cool. Wow. Wow. So this is really good. I'm going to give you my perspective on this. And again, this is my perspective. Actually, I could go back to 1584. This is their perspective as well. IEEE 1584. These documents tell us that whenever we're looking at a piece of equipment, service entrance equipment, a panel board, a switchboard, I don't care what it is, we have to consider possibility of line side propagation. So the incident energy in any panel board, say take a panel board, it's easy to talk about. If I'm looking at a panel board, service entrance panel board with a main, if I have an arc flash event that's inside that panel board, I can't rely that I don't have when you understand what an arc flash event is, it's that plasma, it's that cloud. I call it the plasma plume, and people make fun of me, but it's a plasma cloud that occurs of ionized air, and electricity current flows through air. So what can happen? I'm not going to say it will happen. I'm saying it can happen, and we as engineers, as safety professionals, we have to assume the worst case, and the worst case is you get what they call line side propagation. And what happens in line side propagation is it takes the main overcurrent protective device that's in that equipment out of the picture. It's no longer a part of the circuit. So you can't rely on the main overcurrent device in that panel board to clear the fault and give you how to dress. We go to the next upstream device. Now, in service entrance equipment, I see my buddy Mr. Crawshore is here. You got Tim Crawshore out there on the line side of that of your equipment, and what does he have? He's got a primary fuse, medium voltage fuse, that's on his transformer. He probably owns that transformer, and that primary fuse is not selected for incident energy reduction at that main service panel board that's downstream. That fuse is selected to make sure that the transformer energizes. And if you were in my transformer class, you remember I'm pushing that fuse or breaker to the right because I have to worry about inrush current on the transformer. So I have an intentional delay. I'm at 1.25 minimum probably on my transformer size for that line side overcurrent protective device, and I have an intentional delay. That fuse is not going to limit the amount of time that your arcing current is going to occur, that can occur inside of that panel board. And we have to make a decision. Do we use a 2-second rule? Do I actually give the calculation for however many seconds it takes and get this huge number that I can't design to or work on? But in any case, I would argue that at service entrance equipment, you do not determine the clearing time and the incident energy based upon the main overcurrent device in that equipment. You've got to go upstream. Now, if you've designed your system carefully, your service equipment is hopefully a breaker in a box or a fusible disconnect switch, and then your actual panel board is not a service panel board, it's a feeder panel board, it's a downstream panel board from that service equipment. It's not service equipment, and now you can take advantage of the arc reduction technologies or the capabilities of the overcurrent device upstream. I've got pictures of this to show this, and we're going to talk about this in more detail. My chips are all in the true basket on this one and not in the false basket. I base that on IEEE 1584 and what the guidance that they give that to you. All right. I'm just going to look at the chat before I go to the next one, but not access to the actual code. There are often changes between the preprint and final code. I see some stuff going on with Menti, and that's all good stuff. And Mr. Crawshore, hello there, sir. Thank you for joining us. All right, so I'm going to go to the next question. Line side barriers required by the National Electrical Code enable the main overcurrent protective device to be used to determine incident energy for that equipment. And as you can see, my computer is really struggling today. My internet is at least, but it looks like I still have good connection on TubeLand and whatnot. But in any case, we've got 46 falses, 28 trues, and 8 not sures. My basket, my chips are in the false button. If you think about the line side barriers that were required in Article 230 now for services, which it was in 408.3, it's now in 230. For all service equipment, have to have a line side barrier. That barrier is there for shock protection. Now, I could make an argument that it reduces the likelihood of an arc flash event, but it will not. You can't count on that because you can't count on that for the same reason, the same discussion that we just had. Those barriers aren't listed and tested to prevent line side propagation. So in any case, 54 false, I would agree with those 54. That barrier is there for shock protection. The same information obtained from the utility for 110.24 fault current labeling can be used for arc flash calculations. I love this. Where's my code book? Oh, all right. See, to answer this one, I would have gone to 110.24. I gave you the section. And here's what 110.24 says. 110.24, if you're not familiar, it is the available fault current field marking that you have to mark service equipment other than dwelling units with the available fault current in the field, blah, blah, blah. And there's an informational note. The available fault current markings addressed in 110.24 is related to required short circuit current ratings and interrupting ratings of equipment. NFPA 70E, Standard for Electrical Safety in the Workplace, provides assistance in determining the severity of potential exposure, planning safe work practices, and selecting personnel protective equipment. Now, if I grab my 70E book, there are two methods in here. If I go to there's the calculation method is what you're going to look at, and I believe that's in 130.7. Nope. 130.6. 130.6 is the area where you're going to have your incident energy methods described, and basically what you're doing here is you are calculating incident energy, and we're going to walk through the components to an incident energy calculation. You need you may not just need the maximum available fault current. You may need the minimum available fault current. And remember, 110.24 is a number that a lot of times the utility is going to give you a number. If you ask them for available fault current, they're going to make an assumption that they may not make an assumption anymore, but they're going to give you the maximum, which is going to be based upon the infinite bus on the primary of their or the secondary of their transformer, and that infinite bus is more than likely going to be based upon the lowest impedance of the possible transformer size that they could put outside your building, not necessarily what is actually out there from an impedance perspective. Because if they say, well, I've got a 200 kVA or 300 kVA transformer feeding that facility, what's the lowest impedance that I'm going to get from Eaton, my Cooper guys? And they're going to base their number on that, because if they have to change that out with another 300 kVA transformer of the same size, it's not going to be the same impedance. So they're going to give you the lowest impedance that'll give you the highest, because they're thinking 110.24, which is there for short circuit current ratings and interrupting ratings. Well, if you're using arc flash, you're not necessarily worried about, you are, but you aren't. That's not the only information. Is the maximum fault current that you have. That'll give you the worst case maximum, but you could have a worst case actual higher incident energy on lower fault currents. So the 110.24 marking is not necessarily the number that you're going to need. You're going to need more information. You're going to need the actual fault current at that equipment, which will be lower, more than likely, and you're going to need to get information from. I got a little problem going on. 1 second. Remove. There we go. So you have to worry about the minimum and the maximum numbers, not just the maximum. If that makes sense. So that 110.24, I would steer away from that as being that number for calculations for. And I say arc flash calculations. And I would also say that even if you're using the table method, but if you're at the service entrance equipment, that's like one of the most dangerous places in the power distribution system. It's hard to even apply the table method at that location because you're looking at that next upstream device. But we'll talk more about that one as well as we move forward. I would put my name in false on this one. I'm clicking and it ain't moving. All right, it is required by NFPA 70E to put a date on your arc flash labels. And this is a true or a false. I've got 72 trues and 9 falses. Wow. Let me just tell you something. Anonymity is only good when you have a mix, okay? But when you have such a drastic difference, anonymity pretty much goes outside the door. 75 of you now are not right. 70E does not 70E does not require a date to be put on the label. Now, if I go to, and we're going to talk about 110.16, 110.16b does require a date only if you're putting the bare minimum information of fault current, clearing time, voltage. 110.16b tells us, I'm looking at 110.22. I need 110.16. 110.16b says, in other than dwelling units, in addition to the requirements in 110.16a, a permanent label shall be field or factory applied to service equipment rated 1200 amps or more. The label shall meet the requirements of 110.21b and contain the following: nominal system voltage, available fault current, clearing time, and the date the label was applied. Now, the exception is service equipment labeling shall not be required if an arc flash label is applied in accordance with acceptable industry practice, and NFPA 70E is one of those acceptable practices. But when you go to 70E in equipment labeling in section 130.5H, 130.5, which is arc flash risk assessment, H, which is equipment labeling, it says electrical equipment such as switchboards, panel boards, industrial control panels, meter socket enclosures, and motor control centers, likely to require examination, blah, 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 shall be marked with a label containing all of the following information. 1, nominal system voltage. 2, arc flash boundary. 3, at least one of the following: the available incident energy and the corresponding working distance based on the tables, or B, minimum arc rating of clothing, or C, site-specific level of PPE. And then it gives you 2 exceptions. It says the method of calculating the data to support the information shall be documented. The data shall be reviewed for accuracy, not to exceed 5 years. So that's where we get our every 5 years, you need to update it. And then the owner of the electrical equipment shall be responsible for the documentation, installation, and maintenance. There is no requirement in 130.6H to require a date. Now, you'll say that's a bunch of bull cookies, but that's true. And the other thing is that there were public inputs to add the date, and they keep getting rejected. And I would say don't stop that, because in my opinion, every one that I have ever seen, they all have dates on them anyway. We put the dates on things, and I think dates are there to prevent or to protect people, to protect the person, to protect the facility owner. Because if there's no dates, then someone has to have a report or whatnot, or maybe you don't have the report. Maybe it's with the firm that did the study for you. But in any case, you have to you're gonna want to show that your information is still valid and accurate, And if you don't have that the date on that equipment, then there's no record of when that was done, and that's an important piece of the pie. Even from the electrical workers' perspective, they need to know how old the label is that they're looking at. You walk up to a piece of equipment, was it done yesterday or was it done 10 years ago? It's in my opinion, it's all about the electrical worker. So I would say this is false. 14 of you did a great job. Stand up, because such a disparity. You need to stand up, pat yourself on the back, and run around the room 2 times, and we'll wait for you. Incident energy calculations are not required on 208 volt systems. Okay, everybody's got this is good. That is a false statement. In fact, IEEE 1584, the boundaries go down that low in voltage. So there is definitely, that is a false statement. For the 10 of you who said true and didn't put yourself in the not sure bucket, well, hopefully you learned something today. You do have to calculate incident energy down to 208. There's nothing that says that you shall not do that. Lower fault currents will always drive lower incident energy. False. 64 said false. Excellent. That is a false statement, because lower fault currents can give you longer clearing times. Looks like you guys and gals have your handle around this. I do have slides that speaks to this in detail. So now we're going to the next one. I think the next one was just the opposite. It talked about higher fault currents will always drive higher incident energy values. And the answer to this one, again, is false. Higher fault currents can put you into a faster clearing time in the overcurrent protective device, which will give you lower incident energy. I've had this, and the reason I do this is because I got a call from a customer one time who asked me to help him with, he said he's got a problem with his design, and they were laying the system out, and he had a pretty good estimate of the length of conductors and whatnot. And he said that one area of the power distribution system had high incident energy, and he wasn't sure how to solve that problem, because it seemed like everything they did, they couldn't solve the problem. And I looked at it, and I put it in SKMs, and I ran an analysis. And for giggles, I added another conductor in parallel, feeding that in that feeder, and it cut the resistance, the impedance in half, and it increased the current, the arcing current and voltage fault current high enough to get into the instantaneous region of the upstream overcurrent protected device. So I called him back and I said, you're going to think I'm crazy, and I don't know if you can do this in your design or not, but can you add another conductor in parallel? And he's like, yeah, at this point I can. And he said, why? And I said, well, if you add another conductor in parallel, it cuts the impedance in half and it'll increase your fault current. And he goes, well, that's going to be even worse. And I said, no, you're going to be clearing faster. You're in the instantaneous region now of that breaker, and it will give you a lower incident energy value. And he told me he was going to have to think about that one. And then I believe that's what he did. I can't remember. I believe he called me back. I cannot remember. I had that feeling that he actually did that. But that was it was like almost like a teaching moment. It was a learning moment for me. That changing that conductor out, it was long enough, and the drop in impedance was enough that it actually gave him a decrease in incident energy. All right, so those were the questions. Good job on the questions, and I love when we have the differences of the differences in answers, because that just tells us that we're learning something. So question one, I can't remember what question one was. I believe it was false. Yes, question one was false, Mr. Crawshore. Okay, our utility gives us a calculated value, not the default value. Yes, Richard, Rich, Curran. Yes, so I was doing a presentation, I believe it was in Alabama, and Alabama Power was in the audience. I don't know about other utilities, how they handle this. But Alabama Power basically told everybody in that room that if they are asking for a fault current value because of an incident energy calculation, to let them know, because they will give them what you're saying, Richard, Corinne, they'll give them a calculated value down to that to their facility. Now, I don't know what every other utility does, but I do know I have seen a few utilities that'll say, listen, you tell us what you're going to use it for. And I do have a recipe for when they don't give you that other number. I've got a reference to an IEEE paper that I think might give you some guidance to help you. So I'm going to look at the chat real quick on WebEx. I really wanted to make this one, but no access to the actual code. I really wanted to make this one true with my line side barrier proposals, but that didn't happen. Yeah, I know, Dawn, but you know what? Don't give up on that, because I think that what has to happen is here's my opinion. I look at our line side barriers in our commercial applications, especially. We wrap that with rubber insulation, right? And if you have a fault downstream, I defy it, especially if you're in the instantaneous region. You're not going to get line side propagation. If you're outside of the instantaneous region of a breaker, or you're outside of that current limiting region of a fuse, you're going to get enough plasma probably in the air to propagate. But I would almost argue that in that case, with that wrapping, the chances are much lower. I can't say it would never happen. And I can't prevent a fault from occurring behind that, but I'm sitting there saying, what are the chances of that as well? I believe, though, that change increased safety considerably. And Kevin Ryan noted that's why you have to use multiple scenarios and take the worst incident energy. Absolutely right. And what we're going to talk about are all of the different types of scenarios that you get the high fault currents and you get the low fault currents. And you got to think about what are those scenarios for each of your power distribution systems. And then Vixer, some of our clients would ask us to use 50% of the utility fault current for worst case arc flash if the utility only provides maximum. And I'll tell you what, Vixer, you're going to be happy with the IEEE paper that I give you, because not only is your customer asking you for it, but there was an IEEE paper that verifies that percentage number, and we're going to get to that. So I already spoke a little bit to this. We're going to hit 110.16 a little bit, 240.67 and 240.87 as a direct relationship. And then you have 110.26 and 230 maximum numbers and service equipment enclosures, etc. That would talk about spaces, and I call those indirectly relating those. And I could probably go to a lot of other areas in the National Electrical Code that indirectly relate to electrical worker safety. But I sort of highlight these three in specific. Primarily, you need working space, and if I give you enough space, it'll reduce the likelihood of you falling in or dropping something into your equipment. Maximum number of disconnects changing, permitting me changing the 6 disconnect rule, removing all 6 disconnects. You're no longer going to see a panel board with 6 disconnects inside for service entrance equipment. That's promoting more service entrance main. And I think that if you're in the instantaneous region of that breaker or fuse, the likelihood of line side propagation is lower. So I can make arguments there. I'd love to do some testing. And 230.62 talks about, I'm looking over there, I can look right here. Service equipment enclosed or guarded, and that's that barrier that we just talked about. I also throw into this discussion 225.30. And the reason I do, oh man, I keep clicking, too many clicks. The reason I throw 225.30 into there is because the line side, if I can, what do you call, if I can take a feeder that would have been, say, a 1200 amp breaker and split that into 2 600 amp feeders, my fault current is going to be the same at the end of that run, whether it's a 1200 or two 600s. But what I've done is I've moved my instantaneous further to the left, that it'll pick up on lower currents. So I can provide a better chance of providing lower incident energy at the end of that run. Now you'll say, well, Tom, you got to be careful, because if a 1200 amp worth of feeder conductor has a different impedance than 2 600 amp worth of impedance, because the fault currents will be much lower, because you've increased the impedance now because it's a smaller conductor. And that lower fault current that results could even be more difficult for the 600 amp breaker. But I'll take my chances on that one. And I do agree you'll have to do an evaluation no matter what for the 600 amp breaker versus a 1200 amp breaker, because the fault current at the end of that run is going to be lower because of the added impedance of the smaller conductor. That evaluation will still have to occur, but there is a good chance that 225.30 could help reduce the incident energy as well at the end of that run. Okay, I'm looking at the feedback here on YouTubers. I'm liking usually my WebEx guys are more chatty than my tubers, but the YouTube people are good feedback on there. We got the great pro tip for improving clearing time. Absolutely. The Eaton double door fusible safety switch, smart way to separate the line and load sides. Absolutely. The double door safety switch, they put the actual switching capability up top, and it's even got a barrier, and then down below is where you have your fuses. So when you open that switch, you can't open the top door, you can open the bottom door, nothing in there is energized, gives you good separation. Marcy says the available fault current for the specific site was requested for the installed transformer. Smaller electrical cooperatives will provide infinite bus acting as though they are providing as requested. Typically, the smaller electrical cooperatives have to pay an engineering firm for the calculation to which they try to avoid. That's a good point, Marcy. Very good point. And that's why you really have to understand the data that you're getting. You know, if you read most of the systems analysis studies, they'll tell you you've got to be qualified to even do those calculations, because garbage in, garbage out. And so you got to be careful on what the data is that you're getting, and make sure that you know what it is so that you know how to use it appropriately. So let's talk about what an arc flash event is. And there's no definition of an arc flash event. So I came up with one. It's the light, the heat, the sound, the gases, and you're seeing it right now. I mean, that is an arc flash event. You've got light, you've got heat, you've got gases, you've got pressure. It's a rapid release of energy. And remember, I talked about that plasma plume. You're taking copper and you're vaporizing it. You're creating a conductive environment for current to flow through the air. And that is what's happening in that event. Now, the amount of incident energy that the electrical worker can be exposed to involves current and time. And I'll tell you, based upon the recent editions of IEEE 1584, the current and time is important, but also the size of the enclosure. All right, so I'm going to give you another video here, which is an example again of an arc flash event. I'm giving you 3 scenarios. The first one is about a 6-cycle clearing time, so 0.1 seconds. And you're going to see it's a motor starter. You're going to see the mannequins being engulfed in smoke. You're going to see the pressure that's going to press against the mannequin. And in this example, the gutter that's above the top of the mannequin comes off and hits the mannequin in the head. It's going to be very fast. You may or may not see that in this video. All right, my audio just experienced an arc flash event, absolutely. So you're going to hear it again. This might be a little loud, so be careful. I'm not sure if I can adjust that. So here we go. Holy shit. Perfect. All right, so that, I'm not going to show that again. It's very loud. At least it is in my office here. What you saw was temperatures upwards of 35,000 degrees Fahrenheit at that event, rapid release of vapor, and it's vaporized metal basically that's happening. You saw the pressure wave, and for that mannequin that was standing in front of it, he had more than, anything with a greater than symbol is more than. So you had more than 2,000 pounds, 2,160 pounds per square foot pressure on his chest. The hands, the hands and the neck were pegged at over 437 degrees Fahrenheit, and the temperature at the chest was 122 degrees Fahrenheit, and the sound was more than 141 decibels. So it's a very violent event. And you can say, well, I got to have my personal protective equipment on and I'm okay. But you don't want to be in front of that even if you have the right personal protective equipment. So very important to have the right information in front of you. And that is an arc flash event. Now, the next video I'm going to show you has a overcurrent protective device, a smaller overcurrent protective device that's going to be a couple cycles to show you the magnitude of what that current limitation does, or the current limiting device does, to reduce the amount of energy that the electrical worker is exposed to. So there's going to be 3 videos in here. The second one is going to be a smaller incident energy because I have a smaller overcurrent device in series with it. And here it goes. I'm going to show that one more time. Let me hit it one more time. All right. So, and then now that one you saw a little bit of pressure, but again you had you still had sound, but not as much. The only thing that was pegged was the hands because it's really close. You had 504 pounds per square foot of pressure on the chest. You had no data on the for temperature on the chest. You had 143 degrees Fahrenheit on the neck, and again the hands were pegged, but that's because they were very close. Much more respectable. That's something you can dress for. I mean, after that goes, you're going to have to go home, probably change your clothes, change your shorts a little bit on that one because that's going to be it's still an event to behold, but not as catastrophic as the first one. Now on this next event, you're operating, it's a much smaller fuse. It's right there in that enclosure, in the motor starter, and you're going to see what current limitation does for the reduction of arc flash. And then think in your mind, remember we were talking about the line side propagation discussion? That first event that you saw in this video, very violent, big energy plume, and you can definitely see a line side propagation in that world. And I could make the argument that could that happen? Yes. But now in this next one, when you're operating in the current limiting region of the fuse, I want you to watch this video and think, do you think that could propagate to the line side of the overcurrent protective device? And so I'm going to show this one to you, and I'm going to give this to you on full screen here. We'll show that one more time because okay, so now in that one there, we didn't have any data to record. We didn't, not only didn't we have any data at the chest, the neck, the sound, etc. We didn't even have anything at his hands. The current limiting device can operate so fast, it clears in less than quarter of a cycle, and it can extremely reduce the pressure and all of the smoke and vapor and whatnot to keep the electrical worker out of harm's way. That is what working in the current, that is, when I was younger, I was always I always wanted to grab whatever tool it was, and I would just muscle everything, just try to get it done. And my dad used to tell me, let the tool do the work. Okay, instead of trying to lift it by hand and get 3 or 4 people let's go get a piece of equipment to lift it onto the truck. So let's go get a forklift because we got one right here. Don't break your back. Let the tools do the work. Well, in the case of these overcurrent protective devices, you have to feed them current. When you feed an overcurrent protective device, it will work. All three of those was the same amount of fault current, but three different types of overcurrent devices. Actually, two different. One was a 6-cycle clearing time, 0.1 seconds. So basically no overcurrent protective device in that picture. The other two were overcurrent devices and smaller in nature, and that last one, current limiting fuse, is insanely fast. It barely even moved his hand. Our goal as design engineers, as design build people, we need to get people into daily wear, into gloves, glasses, and light personal protective equipment. And we can if we design the system correctly and we leverage what we know about arc flash and incident energy and current limiting overcurrent protective devices. All right, so let's talk about to understand the information and what we're doing in the world of arc flash and incident energy. We want to calculate incident energy, and we use IEEE 1584 to get that calculation done. We'll make sure everything is working fine. So IEEE 1584 just recently went through a revision. So what you're seeing here is the 2018 version. The previous edition was 2002. And we'll talk about the differences between 2002 and 2018 and what changed as we go through our discussion. But now it's important to understand, just like in anything, you have to understand what are your boundaries? What are your limitations from a calculation perspective? 1584, the 2018 and the 2002 version are valid from 208 volts to 15,000 volts. So that's your range. And remember, they talk about the three-phase line to line. Now, there is a gentleman by the name of Duckie Jacobs. Most of my IEEE people out there will probably know, especially my seasoned IEEE people will know the name Duckie Jacobs. And Duckie Jacobs was an engineer that years ago did a lot of research. And what he showed in a few IEEE papers, and which was confirmed by others later, that if I have that equipment and I have a line to ground fault, you saw what happens. You saw that plume, that vaporized copper, that turns that fault into a three-phase arcing fault within 2 cycles. So when we look at IEEE 1584, they referenced Duckie Jacobs' papers and others to basically say, look, you have a line to ground fault inside that equipment. Your arc flash event is going to send it to a 3-phase arc flash event, and we don't consider a line to ground fault when we do our calculations. We take the 3-phase bolted fault and the numbers and all the data that we see. We're basically taking a little trace wire between the phase conductors or the bus. We're valid for 50 and 60 hertz. And this is the kicker. This next one, this bolted fault current, is that first one, which is, if you think about it, the majority of where probably a lot of the people on this phone operate is in that 600 volt or less type of world. We do a lot more work on that equipment on a daily basis than we do on medium voltage stuff. But in any case, we're only valid up through 106,000 amps. We don't go beyond 106,000 amps in our analysis. So I don't have any way to calculate arcing currents and then take that and do an incident energy calculation based on IEEE 1584. What we do in those cases when we're outside of that 106,000 amp range is we use the Ralph Lee method, which was Ralph Lee was an engineer, or is an engineer, I'm not sure. Back in 1982, wrote an IEEE paper which precedes the 2002 version of 1584 that talked about, the title of it was I think it was The Other Electrical Hazard or something like that. And what he did was he showed how to calculate incident energy based on three-phase bolted fault, but he didn't calculate arcing current. So, reason I keep saying that arcing current is because the 24087 and 24067 require you to show the arcing current either in the instantaneous region of the breaker, or that the arcing current clears faster than 0.07 seconds, or that the arcing current is going to operate and function the arc reduction technology. But if I can't calculate it, I can't show it. So that presents a problem in trying to meet the National Electrical Code requirements in 24087 and 24067. I have some ideas on how to get around that, which I'll share with y'all, but that is an issue that we need to contend with. Here, let me go to the next slide. I think there's the details on Duckie Jacobs. You know, he establishes a relationship between temperature and skin burns. This is like one of the major papers, and it's referenced in IEEE. If you go to 70E, if you go back to the annex, wish I could remember these things off the top of my head. You know, I have a lot of admiration. I admire those who can just rattle code sections off the top of their head. I've got so much stuff up there that if I remember something, I'm going to forget something else. So annex, not F, annex D. Informative annex, let me look at the title of D, Incident Energy and Arc Flash Boundary Calculation Methods. Informational annex D, there's a section D2, talks about the Ralph-Lee calculation method. And it's all documented right here in this reference material in 70E. I'm looking at the 2018 version right now, paper copy. His analysis method is referenced in 70E, and so it's an acceptable method. But I would tell you that it doesn't calculate arcing current. And that will be a challenge. And again, it precedes 1584. Doesn't establish an arcing current value, but it's what we use when we're beyond 106,000 amps. Now, what impacts arcing current? The 1584, IEEE 1584, the 2018 version and the 2002 version. What we know is that voltage and frequency obviously impact the arc flash calculation. The electrode gap, and that's the gap. If you think about a piece of equipment, say it's a panel board, a switchboard, or whatever it is, you have A, B, and C buses, and then there's gaps between line to ground and between them. They're talking about that gap, and different equipment will have different gaps. So in the 1584 base equations, they give us the information that we need to calculate for each of those types of equipment. But you may come to a manufacturer and them say, our gap is different than what's in 1584. That's perfectly fine. You may look at it and say, I measured it, and the standard says 100 millimeters, and I looked at it and it's only 80 millimeters. Hey, if you can document that and you can provide that as part of your study, that's perfectly fine. There's no rules and requirements that says it has to be the gaps that are listed in 1584. But it is more work on everybody to try to figure out what the gaps are if you're not going to use the standard numbers. Now, what they added in the 2018 version of 1584 is the electrode configuration. What that is whether or not that electrode is facing you, coming straight at you, like you would see, say, on a utility transformer, those big green boxes that are on the ground where they have those stabs that stick out. That is the bus is staring you in the face. Panel boards are an example of a horizontal bus where you're looking at the copper bus or the aluminum bus in a manner where it's vertical. It's a vertical bus that is going up and down instead of horizontal, pointing right at you. So we know that the electrode configuration, but those are the only things that will, and obviously the amount of fault current that you have. But the electrode gap, the electrode configuration, voltage and frequency, 4 key parameters. The size of the enclosure does not impact the arcing current calculation. The size of the enclosure will impact how much energy you see in front of the equipment. All right, I'm going to look at the chats here real quick. I see somebody just put a really big chat in here. Gabe Paletti. Evaluation notes: to match the selected short circuit method, added a global toggle for switching between protection functions, improved time adder, integral trip units, resolved frequency, fault current, TCC plotting issues. I'm just looking through what all of that stuff is. I'm not going to read all of that. All right. So, and Brian Rock's in the house, y'all. Thank you very much, Brian, for showing up. And I see you copied 130.5G out of there. Incident energy analysis for not to exceed every 5 years. How can that be enforced if the date isn't marked? I agree with you, Brian, 100%. And I even said, I'm not on 70E, but for the last, I don't know how many cycles, I sat around the table, and after that debate, I would go up to people and say, I don't understand why they voted against it, because, how do you meet 130.5G and to know that you need to update it? And their pushback was, well, you have an analysis study and the study itself has the date. Well, yeah, I get it, but, you should go out to, and the more you propagate that date, the better off you are. And the pushback is, well, now I got to go change all the dates on all of those labels. Well, yeah, you have to change the dates, and you're probably going to have to change the numbers, right? But in any case, it failed. Tim Krauscher says, Tom, does Bussmann make K5 and K9 current limiting fuses? I believe we do. I'd have to take a look, but I believe we do. I believe so. I don't know if many of my Bussmann guys are on here. I'd have to get my catalog out. I've got OCPD issues. I've been with Eaton since 95 for 20 some years, 24 or whatever years. And I've been with Bussmann for about 5 or 6 and in the Bussmann division. So I argue with myself. I say I have my OCPD issues. I'm not as my breadth of the product availability is pretty limited there. I'm not sure if it's if we have that, Tim, but I will do that research for you, buddy. Okay, let's go to the next slide here. 1584, the first step. Now, this is the first step, is calculating that 3-phase bolted fault current value. In reality, you also need the accurate one-line diagram. So you're going to need the one-line diagram, the impedance diagram, which you're going to develop, the system configurations, and the equipment ratings. You're going to have to do your equipment ratings and make sure that your equipment is applied correctly. Now, we talked about that utility current, remember? And we said that the utility is going to provide you that maximum amount of fault current, which is not really what you need. There was an IEEE paper done. The title of it is Impact of Available Fault Current Variations on Arc Flash Calculations. For the IEEE members out there, if you're an IAS member, you can download that from IEEE very easily. What else here? So, and if you just look at the conclusions, they said that in the middle paragraph the second paragraph let's read that one. This paper demonstrated that performing an arc flash hazard analysis using only an infinite bus scenario does not provide the most conservative results for all equipment locations. When no fault current information is available from the utility, and I would say no fault current, I would say if you didn't get that actual number from the utility, the arc flash hazard analysis should include a second scenario where 50% of that maximum secondary bolted fault current is used as the available fault current from the utility. So cut that number in half. And what that's going to do is going to lower your arcing currents, and it's going to give you a longer clearing time. So that could be your worst case. The worst case between those two scenarios should be used as the conservative value to publish and put on a label. So, and that's an IEEE reference paper. That the nice thing about an IEEE paper is when it's published and it's a part of IEEE Explore, that paper has been vetted and been reviewed, third peer you're peer reviewed. So it's gotten peer review and it's an accepted method to use. Although it will produce some, it's going to obviously produce some higher numbers for you. But it is, and if you read the paper, if you download, if you're not an IEEE member, you're gonna have to buy it. It's not that expensive. It's probably $30 or whatever. But it does give you a lot of information because they collected data from a lot of different studies to come up with those conclusions. So you calculate the three-phase bolted fault, then you calculate a minimum and a maximum value of arcing current. And that arcing current, we saw what happens is that current that flows through the electrical arc plasma. That's that violent explosion. It creates that plasma. It's the current that's flowing through the air, and that creates an ionized cloud, which creates and adds impedance. So the parameters that you need, because you need that minimum and maximum number, you're going to need that variation from the utility. You're going to have to think about what motors are on versus what motors are off. Turn motors on and off in your scenarios. Maybe a scenario is all motors are off in the facility, even if that's even if that's not an accurate representation, it'll give you that lowest number. I've heard people say, "Oh, I look at these IEEE, look at the engineers' study and all of these assumptions." They're basically saying they don't know what they're doing. As engineers, we need to make these assumptions to give us the worst case scenario. We don't want to make people underdress for an event. So transformer impedances, we talked about this in the transformer class that we had, that the impedance that's marked on those transformers can be plus or minus 10%. So we have to include that minus and plus number to get both worst cases. Your conductor impedances. And the reason I put the conductor in there is because a lot of times we'll do our analysis in the beginning based upon we're not really sure of what the system's going to be. So we create and estimate our conductor lengths. So it's important for us to do our analysis after the as-built drawings are published and update all of our studies once we have the as-built done. And then the system configurations, and that was pointed out over here on our chat section on WebEx, and also pointed out up here on our YouTube, on our tubers. I'm not sure about Facebook. Oh, yeah, there we go. So we got, I think I'll stay with, yep. So we got some people commenting over here on Facebook as well. But you need to figure out, for example, double-ended switchgear. If you operate at any time with that tiebreaker on, you need to figure out what the worst case is. Maybe both utilities on at the same time. Or maybe the worst is when you only have one utility on, and maybe it's the weakest source utility. And it could be that, hey, you know what? I have an emergency system and I have a generator, and I have much less fault current from the generator. That might give me my worst case. So when I'm from an instant energy, because the generator is not as stiff as my utility, and my arcing currents are in the dirt. So in any case, that is an important piece of the pie. Okay, so once you know your fault current, then you have your maximum and minimum arcing currents. The next thing you need to do is you need to establish the clearing times of both of those currents. And the clearing time is going to be based on the upstream overcurrent protective device, not the downstream overcurrent protective device. We talked about that line side propagation point. So when you look at your analysis, and SKM and EDSA and Easy Power and all of those tools, they will all basically do give you a configuration in the software to ask you how you want to do this. Do you want that line side? Do you not want that line side? And there may be various scenarios, various pieces of equipment that when you model it, because of how it's constructed, you're going to say, well, this equipment, I'm going to not take the line side assume the line side propagation, take credit for that main overcurrent protected device. I usually just do it both ways and then just pick the numbers that I need based upon my knowledge of the system. But you're going to need a coordination study done, which I don't talk about here. The selective coordination study, you need to pick your overcurrent devices. You're going to, if your customer wants selective coordination, you're going to need to put intentional delays in certain areas. You got to get all of that done. You got to make sure all of your equipment is rated for the available fault currents. You have to make sure that all of your equipment and your overcurrent devices have the right delays to give you the performance that you need from a coordination perspective, and then you do your arc flash calculations. Because if you, for example, this is a 1200 amp Bussmann KRP fuse. If you go, I'm going to go with a different size fuse, I'm going to go with the next size up, or I'm going to go with the next size down, that's going to change your incident energy calculations. And if you made that change because of your selective coordination needs, that's going to impact your calculations. Your trip units on your circuit breakers are programmable. You're going to need to know what are those settings, and those settings are going to be determined by your selective coordination. Now, if you don't care about selective coordination, your application doesn't have, you don't care if you take the whole facility out, you're going to put everything at minimum, you don't care if it cascades, then, your study is going to reflect that. Make sure that nobody makes an adjustment because the inrush current on a transformer or the inrush current on a motor was tripping your device, and they went out in the field and cranked the short time delay up to add the delay to let the motor run. And what they just did was they increased incident energy because they're changing time with regard to the arcing currents. So you need to know your fault currents, you need to know your arcing currents, you need to establish the clearing time. And what the next few slides show you are the clearing time and incident energy numbers for 3 600 amp breakers: a molded case circuit breaker, an insulated case circuit breaker, and a power circuit breaker. Think about it, these are 3 circuit breakers. One is bigger than the other. I can't carry a 600 amp power breaker, but I can easily carry a 600 amp molded case circuit breaker. Why would I want a power breaker over a molded case circuit breaker? It's going to be much more expensive. It's going to go in bigger equipment. It's because I need a time delay upstream. So this is a 600 amp molded case circuit breaker with a maximum arcing currents of 29,600, minimum arcing current of 25,900, calculated based upon IEEE 1584 2018. Both of the clearing times, and you'll notice on this one here, the clearing time at 29,000 is 0.625. The clearing time at 25,900, which is the lower number, is 0.75. So the calculated energy is based upon the 25,900 amp value, not the 29,600. And this is 0.64 calories per centimeter squared. All right, you're in daily wear. You're less than 1.2 calories at that point, which is a good thing. Now I take that 600 amp breaker and I put a insulated case breaker that has an intentional delay. It has a short time delay feature capability. The instantaneous is further to the right. Why would I want to push the instantaneous to the right? Why would I want to delay? Selective coordination is one reason. Motor inrush or transformer inrush is another reason. We saw those curves in my transformer class this week. Now my clearing time for both of these fault currents is exactly the same, 9.6 cycles. So now the higher incident energy is going to be based on the higher fault current, and this yields 12.7 calories. So I went from less than 1 calorie to 12 calories. Both of them are still 600 amp circuit breakers. One is a molded case, one is an insulated case. So now I changed that 600 amp insulated case circuit breaker, and I'm going to add in a 600 amp power circuit breaker. I still have the same clearing time because now I'm 30 cycles, and I am at a 0.15 second clearing time. And now the 29.6 is going to be my higher fault current, same clearing time. That is where my 31.8 calories is coming from, that 29.6 thousand amps of arcing current. 31.6. So what we just went through, we went from 0.6 calories to 12 calories to 31 calories, almost 32 calories. All three are 600 amp breakers. All three of those have different clearing times. So when people ask about different types of overcurrent protected devices and will one give me a different number, it's all about the current and it's all about the clearing time. Now, we talked about the scenarios and we said, well, motor contribution is going to be different, right? So the motor contribution, you have to understand that if I have a fault in this system at this point in the system, my utility, or I can call it utility, but it can be any upstream source, really. I mean, this doesn't have to be service entrance equipment. It could be down in my facility, and that could be just a feeder. I have fault current coming from the upstream equipment that comes through that main overcurrent protective device, and it is contributing fault to that system. Now, when I turn those motors on, I am going to have fault current contribution coming from each of those motors downstream. But the key thing to remember is that motor contribution does not flow through the main overcurrent protective device. Those currents, the motor contribution and the fault contribution from upstream, which could be the utility, they add to contribute to delivering fault current to that system. The clearing time in this case is not based upon the total fault current. The clearing time is only based upon the fault current coming from the upstream overcurrent protective device, because that's the fault current that flows through that main overcurrent protective device it's the one that's on the primary of that utility transformer or the upstream device, right? So the fault current flowing up, hold on. I gotta go back because I almost broke my own rule. I know there's probably people going, he said that he can't take credit for that main overcurrent protective device. And you're right. My clearing time for this event, my board is falling. Sorry for shaking everybody. My fault current is actually coming through that transformer. So the overcurrent device up there is the device that is what I would use to base my clearing time on in this application, right? But the motor contribution does not flow through that upstream overcurrent device. It's downstream. So my total incident energy is based upon all of that arcing current, all of those electrons running to the party, right? Because they're party animals and they're taking that fastest route. But the clearing time is only dependent upon the fault current that flows through the upstream device. And in this scenario, it's the clearing time of what's on the primary of that transformer. Hopefully you understand that. So when there's no downstream motor contribution, then my clearing time is based upon the available fault current at that location. Done. Does that make sense? I'm just going to look and see if there's any notes coming in on WebEx. These are SKM updates on their software update. Oh, okay, gotcha, Gabe. Thank you for putting that up there. In a hospital, maintenance would have records of everything. Is it a joint commission? Yes. Good point, Kevin. The joint commission requires them to do maintenance. But almost all the labels still have the date on it. And in my opinion, the date covers your butt. It covers your butt. Some people may say that's an added liability. I think it covers your butt because it shows that if the worker was out there and he was doing his work and the date and that label was old and he didn't follow whatever, they can say, well, you didn't have the date on it, but he followed the rules. So now the owner's got to defend that label, that it was an old label that was out there and the study was updated, but the label wasn't. But then you can say, well, I have the label and I have the date on it, but I didn't keep it updated because I updated my study, but I forgot to replace that label. Well, yeah, but you're at you've got to be thinking about the electrical worker, in my opinion. Putting a date on the label is an NFPA, isn't it? No, it's not, Henry. It's not an NFPA requirement. Uh, Only if you're in 11016, 11016, we talked about this earlier. 11016, if you do the option that's in the parent text of marking the fault current, marking the clearing time, etc. If you fall back on an industry practice, which is falling back on 70E, 70E does not require the date on that label. All right, I'm gonna look at my YouTubers. I had to quiet a couple people. I got to keep my eye on that. I got rid of a couple messages. All right, so everything looks good out there. Okay, here we go. Now, the one-line diagram is critical. You got to have an updated one-line diagram, because if it's not updated, and I would say, on a new installation, you have your design. You haven't purchased anything. You haven't installed. You haven't pulled one piece of wire yet, but yet you've got to quote a job, or you have to figure out. You're going to ask a manufacturer to quote a job, or you're the design contractor and you've got to quote the job, and you've got to put the pieces and parts together. You got to meet your selective coordination requirements if it's an Article 700 system. So you're going to have to do a little preliminary study. And if your customer has, like in some cases, we had cases where the customers has a facility design goal to put people into 2 levels of PPE. I believe one level was like 8 calories and another is 40 cal. And they train everybody for an 8 cal world and a 40 cal world. And you want to be in that 8 cal world, and they may put in the design that, hey, my system, all of these panels have to have 8 calories or less. Well, that means you're going to have to do an analysis. You're going to have to take a look at your system and know whether or not you're at 8 calories or less. Well, and since we know fault current is dependent upon conductor lengths, impedance of transformers, and all this good stuff, you're going to have to make some conservative assumptions, pick your overcurrent devices, but then in the as-built phase, you're going to have to run those studies again, because the conductors are probably not going to be the same length. The transformers are going to come in at different impedances. Your motors are not going to have from a motor and generator perspective, they have some transient reactances that you're going to be using that are going to be different. So there's a lot of things that can change, and you need to update this per the as-built drawings. Very important and very critical. And then if you have things like this, where you have double-ended switchgear, you have motors that can be turned on and off, you've got to think, what is my worst case and what is my best case? What are my 2 cases? What will give me the highest fault current? What will give me the least fault current? And use your head on these things. Now, I mentioned turn all the motors off. Well, yeah, you could do that. Is that realistic? Probably not, right? So you've got to make things realistic, because you can end up just creating labels that aren't realistic and puts guys into 40 cal outfits, and that in itself creates a hazard. Overdressing for a situation is not the greatest thing either, because you're restricting the movement of your electrical workers, the tools they're using, and all of this stuff. So you want to make sure that anytime you change your power distribution system, anytime you add motors and subtract motors, you have to understand, go back to my fault current class from a few weeks ago. What impacts fault current? You add motors to a system, that'll increase fault current. That could increase or it could decrease incident energy. Subtract motors from your system. That could will decrease available fault currents in some parts of your distribution system, and that could increase incident energy. When you change your power distribution system, you need to update your studies. When you and 70E tells us, remember, 5 years or when the system changes. So you may have to do it more frequently. Very important part of that piece of the pie. Okay, just checking over here. Looks like Brian Rock. Thank you. You're keeping house, buddy. Brian and I are on Code Making Panel 2. We kick butt every cycle. We work good together. He's a good guy. Sometimes, especially when he's buying me drinks, that's the best time. So thanks, Brian, for chiming in and sharing some information both on Facebook and on YouTube. Vernon Lippert, you need to go out and replace labels every 5 years in a large industrial facility. That will add several days to the update process. We have not had issues with keeping the most recent study on file and available to anybody who wishes to review. Very good, Vernon. I understand the argument on both sides of those, and especially in those worlds where you have a controlled environment. And I would even say put an put a put an exception in for heavy industrials. I don't know where Vernon, what kind of facility that you're in, uh, but if it's a heavy industrial like a petrochem or whatnot, those environments, nobody is going to do electrical work without a safety plan, a hot work permit, and all that good stuff, right? So there's going to be a lot of work done up front. But you take that McDonald's, or you take that other that other facility that doesn't have those qualified people. You're going to have an electrical worker out there. They need, I believe, a label that's up to date. At least with VFDs being pretty ubiquitous on larger motors, motor is not as bad. Yeah, the variable frequency drives, another good point, which I'm not even sure if I think I covered that in my short circuit class. But variable frequency drives give you that shield, right? Because that fault current, that motor contribution is going away. So you take a facility and you say, I'm going to change all of these out to be driven by variable frequency drives. Now you are reducing the available fault currents because you don't have that motor contribution, although you still have that same size motor there. The VFDs don't push that current back onto the system. They isolate that motor. Good point, Vernon. Very good point. Thanks for chiming in. And the other thing to keep in mind as you're doing your arc flash studies, and I said this once, I said it again, I'm going to say it, and I'm going to give you a picture, that if you're calculating incident energy in that panel board, you've got to base the clearing time on the next upstream overcurrent protective device. And it very well could be that in between these two devices is this big hunk of iron that is taking voltage from one level to another, and we call that hunk of iron a transformer. And the moment that this panel board is on the secondary of a transformer, that is the most dangerous location in your power distribution system to work, because you're relying on that primary overcurrent protective device. I can't stress that enough. I was with a heavy industrial customer, and I asked that person, from a safety perspective, what do you lose sleep about the most? And his comment was that first panel board on the secondary of a transformer. And he commented to me, he said that they use a lot of one-to-one transformers, isolation transformers, or one-to-one. And they use that because they have a lot of drives and those types of loads, so they want to isolate that power flow. And because you've added that transformer, that primary device, because of the inrush, that primary device is going to be greater than what you would have on the secondary. So if it was a normal 600 amp run, I put a one-to-one transformer in there. That means I've got 600 amps of full load amps there that I can still supply. The primary breaker can't be 600 amps anymore. Take my transformer class that I have got up there. I've got to worry about inrush. I'm going to be at 1.25 or maybe higher on the primary overcurrent device, which adds that delay, which will give you a higher incident energy on the secondary of that transformer. So here's an example. I have and I call it a utility, but I've got a primary fuse on this in this application. The incident energy in this service entrance equipment is going to be based upon the clearing time of that fuse. And this was an actual case. I had an SNC fuse, I had a 1000 kVA transformer, and I was doing an analysis for a customer. And I just used my little diagram that I sent him as in my class and for this. But this that number, the incident energy is going to be based upon that primary overcurrent protective device. Now, if I do this, if I put a breaker, if I take the main out of that breaker, out of that panel, I take the main breaker out of that panel and I just put it right here. So now the incident energy that's in this panel is based upon the clearing time of that overcurrent protective device. I have just solved my incident energy problem, because now I'm basing the clearing time off of that overcurrent protective device. And what I'm going to do right now is I just want to take your typical transformer. Is that your typical transformer? That's typically what we see, right? I mean, that's an actual picture. I did take that at a location. I'm not going to say where it was. I'm going to hide I'm going to guard the location just as much as that transformer is being piled on right now. This is what your transformer probably should look like in a nice, clean environment for good reasons. If I look at that scenario, my incident energy in that secondary panel is going to be very high because of the fact that I have to rely on that primary overcurrent device. But if I put a fusible disconnect switch, or if I put a breaker in a box, I don't care if it's a fuse or a breaker, I'm going to reduce the incident energy at that first panel board. What's the likelihood of me getting into this secondary panel down here is very high. What I've basically done is move the energy level from that panel up into that disconnect switch, which I will rarely, if ever, have to get into that disconnect switch. Now, so here are some numbers for you. This is, I've got a relatively small 250 kVA transformer and a pretty good, accurate ballpark range of an impedance. I've got two 350s on the secondary, two 3/0s on the primary, and I show you my conductor lengths. I think I took this from a job, basically. And I'm not trying to create something in my little analysis here. I'm not trying to be funny. So the incident energy at that panel board is 23 calories. If I'm getting in that panel to do any justified electrical work, if I have to measure my current for whatever reason in that equipment, I've got to do any justified energized work, take the panel off, I'm looking at 23 calories worth of energy. If I simply move that main overcurrent device and put a breaker in a box and put it separately, or if I'm lucky enough and I grabbed my Eaton sales guy and he gave me this breaker integrated transformer where they have the breaker integrated with the transformer, and I buy that as one unit, now my incident energy at that panel board, which I will probably get into a lot more often than anything else, is now 0.34 calories. I went from 23 calories to 0.34. That to me is humongous. And it's a simple change. You just moved a breaker outside of that panel and put a main lug only panel. And I've heard some people say, well, that's so much more money. It's not, I haven't priced it out, but especially if you're integrating it with the transformer, you reduce the cost of putting another box on the wall. You've reduced the space because we put the breaker in that transformer, and all we did was we increased the height of the transformer, so the footprint's the same. But if you really want, if you want to take and get real fancy with it, you say, well, I'm going to put a fusible disconnect switch in there. Even if it's an existing facility, even if you're going to say, I need to get that below 8 calories, that 23 calorie panel board I have sitting next to that transformer. How do I fix that problem? Put an AC disconnect, or not AC, put a disconnect switch, a heavy duty disconnect switch with a fusible switch in there, and you have solved the issue of your incident energy. You took it from 23 calories down to a quarter of a calorie. Luis, Diego, you said if the breaker is integrated in the transformer, why did I have 25 feet? Let's go back. In here, you'll notice, so what I did in this one, you'll notice I have 5 foot and 15 foot. The breaker integrated with the transformer there's not 5 foot of conductor. You're right. I could take some of that conductor out. Here's a picture of it right here. So you do have some conductor. Your breaker is up here at the top, and you do have some conductor on the primary. It's definitely not 5 foot. It's very, very small, probably negligible to your point. So you could eliminate that from the get-go. That's definitely a good valid comment, Lewis. Thank you very much. You were right. I could take that down. I could at least put, because the system, if when I look at SKM, I can't connect the transformer straight to a fuse or to a breaker. I have to put something in between there for an impedance. But I could, to your point, I could put 1 foot worth of conductor or a foot and a half or something that's a little bit more realistic and still put my 15-foot or 10-foot or whatever that's on the secondary of that breaker to get you to the panel board. So, and that will change the fault current. It will go up, but it will not increase my incident energy all that much. But that telling you that, to me, from a design decision and incident energy calculation, that is going to offer a lot of good in our systems. And if you took that practice up there at the service as well, think about it. If you just said, I'm going to put I'm going to have one overcurrent device as my service entrance piece of equipment, and yeah, it's going to be 2,000 amps or whatever it is, or if I split that into 3 breakers in a box or 3 fusible disconnect switches, feeding a main lug only panel, you have increased safety by reducing the incident energy. How do you accommodate the heat contribution from the transformer on the breaker? Mr. J.S. Whitney, that was a challenge. We did the testing, and based upon the inside, based on the inside of that, we do our heat rise tests. We do pass the UL standards for that. But I can tell you, based on what I learned about that after the fact, it was a challenge to get that done. But it can, and it was done, and we were able to get that through all of the UL standards for heat rise. So I don't know if it's because of the size of the enclosure that dealt with it, the fact that it's up at the top and you're close to the vents and the heat is escaping. That's why it's really important in transformer applications. I know we can't control this, but these types of scenarios are ungood. Okay, those are ungood. All right, so I'm going to take a look at some of the chats. Geo, Brian Rock, what happens with the breaker in the transformer? One will have to do an incident energy calculation for that breaker. Yeah, so what you would do you wouldn't do it for that breaker. Remember, so let's take a look at that application again. When you're looking at this type of a breaker in an enclosure, you got to think, what work would you be doing inside that transformer? Number one, why would you have to take that front panel off and get in there? Maybe to do some maintenance. You would have to turn and de-energize that transformer anyway. But then you're going to have to test for voltage potential based on 70E, right? You're going to have to test and see if it's energized or not, and that's going to get you in front of exposed. The arc flash calculation is going to be based upon the primary overcurrent device. At that point, your arcing current is going to be greater, and you'll have a better chance of being in the arcing in the instantaneous region of that main breaker. But actually, no, you don't have a better chance. I guess you could. It's going to depend upon the difference between your inrush current and your arcing current. Remember, your arcing current is going to take into consideration the coils and all that other good stuff. So your energy in that transformer indeed will be just as high as it was as if you it didn't have the breaker in there, because you've got to think about the secondary lugs and the primary lugs and all that good stuff, and calculate the worst case load based on the primary and secondary. But how often will you have to get into that transformer, as opposed to how often will you have to get into the panel board that's downstream? That is how I would go and address that. And if you're going to get into that transformer to do anything, I can't think of any. I can't think of anything that is that I would do outside of thermal that you would have to have it energized. So the likelihood of you having to do justified energized work is probably very little. Geo, is the breaker in a totally segregated compartment? It is. That's all open in there. I can see straight down through there, so it's all one big enclosure, Geo, inside that transformer. One big enclosure, buddy. I'm just checking to make sure. Take a look. To follow up, if arcing current and trip times are the same, regardless of the main breaker being inside or outside of the panel, is there still a benefit to the external main breaker? From Gabe Paletti. There's, you know what? Here's the thing. There's always a there's a benefit in a couple different things. The fact that you have a local way to turn that off. I could make two arguments in that, Gabe. I could make two different arguments. If I am in this type of a scenario, if taking the main breaker out of this panel here and putting it down here in this transformer would make it more likely that I would turn that breaker off to work de-energized on that secondary panel board and not just turn the main off. Because remember, if I just turn the main off, I still have, there's no requirement for line side barriers here. I still have energized conductors landing on the line side of that main breaker. So that's still exposed unless you took that step above and beyond and put barriers up there. So you still have an energized. So you want to promote de-energizing that entire panel board. And I could make an argument that by locating your overcurrent device in this and taking it out of here will increase the safety because you're driving the electrical worker to de-energize that entire panel. I don't know if you agree or disagree, but I could make arguments on both sides of that. You can yes, in this panel, you could kill this whole transformer by turning the breaker off here. Now, provided, now you remember how many breakers are in here. You got to make sure you turn the right breaker off when you're doing that work. So in this scenario, there's a lot of different ways to kill that cat, and I guess the key, killing the power is not as much of the benefit as if you have to do justified energized work in that panel board. Because if you're doing justified energized work in that panel board, putting the breaker on the secondary in this location here will give you a lower incident energy value on that panel. Actually, I got it backwards. I was just looking at the size of the conduit. The bigger conduit is over here. So this is your secondary panel board, not that one. This one's the primary and this one's the secondary. So in any case, putting that breaker in this transformer will reduce the incident energy at this location for justified energized work. Okay. Receptacles below the panel are also a clue. Yes, receptacles below that panel are also a clue. Thank you, Kevin, or Ryan, however you go. It seems adding a circuit breaker integral to the transformer will cause confusion to what is isolated when open. It could. I would say it also. I could argue that knowing which one of these breakers actually turns off that panel board also adds a little confusion because you've got maybe, I don't know, 15 different options here to turn that panel and de-energize that transformer. And over here, if you label it correctly and you tell it and you give the proper indication, you have one solution and that's it. So I could argue that both ways, but I understand your point. Definitely understand your point. Okay. I showed you the examples there and we talked about that. Let's talk about now that you've calculated the arcing currents, now you have to get into calculating the incident energy. And this is where the size of the enclosure makes a big difference. You know, obviously your arcing current makes a difference, the clearing time makes a difference, the electrode configuration makes a difference, but now your the size of that enclosure, the smaller the enclosure focuses the energy out. The larger the enclosure, not as much energy will propagate. This is what we call vertical electrodes in a metal box. So it's termed VCB. You have a gap in between here. So the energy, remember, the arc always flows away from its source. So the arc is going to come down. You're facing, and you're looking at this flat bar. It's going to come out and then plume. I call that a plume. That's just the way I am. So that's a vertical VCB, vertical bus. Now, the other option is a VCBB, vertical bus with a barrier. And in that case, you're pretty close to an insulated barrier. And what you're seeing now is the energy is pushing out towards the electrical worker. This does a couple things. It will increase your arcing current because it decreases the impedance, and it increases the pressure that the electrical worker experiences. But the good thing is increased arcing currents will clear faster. So that can help offset some of that energy. Now, the worst case scenario is what they call a horizontal bus. And in this case, you're looking at the bus. And remember, the arc flows from the source towards the arc along that bus, and that is now pointed right at the electrical worker. So I had a discussion with a gentleman earlier this morning about this, about, from an electrical worker's perspective, what do you need to understand? I think this basic principle is you need to understand if you're looking at a vertical bus where, like in a panel board where things are going up and down, the arc is going to flow in a vertical manner, which is perpendicular to your body. But in this case here, a vertical, like if you're looking at a transformer, if you're looking at an MCC bucket where you've pulled that MCC out, or you're the bucket out, and you're looking at stabs, or you're in a switch gear and you're looking at bus work where it's facing you, now you're in the worst possible location in that equipment, and you're seeing the worst possible energy because that energy is going to be propelled straight towards you. Even more so than worrying about the size of the enclosure. In reality, the orientation of that bus is really important. The new 1584, the 2018 version, talks about open air, vertical electrodes, open air. So that's like your outside construction, more of your medium voltage applications. And this is that transformer application I was telling you about, where you have that green box and you take that transformer front off where you're landing your wires. Those electrodes, those terminations are pointed straight at you. Now we'll talk a little bit about 24087. Again, 24087 has been around since the 2011 code. It started in the on breakers for breakers without an instantaneous, and then they moved over to fuses effective January 1st, 2016, January 1st, 2020. Whew. Yes, it is not just de-energizing, it is establishing an electrically safe working condition. Roger, you are absolutely right. I looked up and I saw your comment on YouTube. That is absolutely right. You got to remember, we don't talk about de-energizing it. We have to establish an electrically safe working condition. So that means you have to take that dead front off and you need to measure and assume that it's energized. So now, from a 24067 perspective, what I'm going to remember, it applies to 12 fuses, 1200 amps and above. And what I want to jump to is the fact that you need to know the arcing current as a part of this language, because you have to show in 24067 that your fuse operates 0.07 seconds or faster. So you need to do an evaluation, and if your arcing current, if your three-phase bolted fault current is greater than 106,000 amps, it's hard, you can't do that comparison. So what we did was we created a tool for everybody, an online tool that can be used on your phone or online. It's an arcing current calculator, and we went and compared all of our fuses, 1200 amps and above. So if I have 106,000 amps, or if I have 150,000 amps on a 1200 amp fuse, I know that it only takes 21,000 amps. 21,000 amps of bolted fault current for me to be in the 0.07 second clearing time or faster. So I know for that 150,000 amps, I am clearing faster than 0.07 seconds. I don't need to do anything else other than say, look, any fault current, bolted fault current greater than 21,000 amps, I have a clearing time faster than 0.07 seconds. That will be enough for the AHJ to understand that you meet the requirements of 24067 and you don't need to apply an arc reduction technology. But when you get up to a 3,000 amp fuse on a 480 volt system, I need more than 106,000 amps to get into the arcing current region. So in that area, I don't have a way to show my arcing current is going to operate fast enough. So my conservative nature of me says that I need to automatically just put an arc reduction technology there. But my second challenge is I can't verify that my arc reduction technology will work unless I simply compare it with the arcing current at 106,000 amps. Or I could take, for example, if I have a 4,000 amp fusible switch and I need to, I have 150,000 amps, I'm either going to apply the arc reduction technologies and then compare that with the arcing currents at 106,000 amps that I can calculate, or I'm going to take that 4,000 amp fusible switch and I'm going to separate that into two 2,000 amps. And now I have 150,000 amps on a 2,000 amp switch, which I know it only takes me 24,000 amps to get a clearing time of 0.07 seconds or faster. And now I don't need to provide a technology. I can provide this evidence to the AHJ. I don't need to do anything with regard to 24067. So that is an important aspect of how to deal with this section in the code, right? So again, you know, and there's ways. If I look at the actual language in 24067, it says fuses rated 1200 amps or higher, and then it says that I have to have a clearing time of 0.07 seconds or less. If I don't meet, if I have a 1200 amps or greater fuse, and I don't have a clearing time of 0.07 seconds or less at the available arcing current, then I need to employ one of those options. The app tool is Eaton's arcing current calculator, and it is right here. So if you go to Eaton's website, type in arcing current calculator, or if you go to, I believe your mobile app, you can get access to this calculator. And basically, you're putting in the information, and it'll tell you whether or not your fusible solution needs an arc reduction technology or not. Makes life easy for you. Now, if you have more than 106,000 amps and you are on a 3,000 amp or greater fuse in a 480 volt system, your arcing current at 106,000 amps is 42,000. Your arc reduction technology needs to operate at least at 42,000 amps or less, probably less. You're probably going to have a set point at a multiple. If it's a 6,000 amp fuse, you're going to be somewhere around, I don't know, 2 times, you're going to be picking up at 12,000 amps, which is much less than the 42.2 thousand amps. And if you're at a 208 volt system, notice how much lower the arcing current is. So you're at a smaller fuse, and I think you're somewhere around a 1600 amp fuse and greater that you need an arc reduction technology on at 208 volts. And the technologies that you pick, remember the differential relaying, you have to understand that each of these are going to have a zone of protection. Differential relaying only protects you for faults in the zone. If you employ an arc reduction maintenance switch, it can look outside of the zone of protection, but it depends upon how much arcing current you have, right? If you're doing the active systems, these are your arc quenching systems. And I think GE calls them their arc vault systems. They also work in the zone of protection. Your arc flash event has to occur in that zone of protection. It doesn't protect you downstream. And then let's take a look at boom. Let's take a look at the circuit breakers, right? Circuit breakers are the same deal. You have the 1200 amps or adjustable that you have to worry about and think about. We already talked about 110.16. I know we got about 6 minutes left. I'm just looking through some things. Let's take a look at some of the, before I go on to any other topic, let's take a look at some of the questions. Oh, you know what I'll do here is I'm going to do a file, new window, file, new window, and I'm going to bring this over, and I'm going to go Bussmann arcing current calculator. And I'll show you guys how to find it. So Brian, and the way this arcing current calculator works is it's more of a web based that you basically put onto your Android or iPhone or whatever it is that you have, and it's not a self-contained app, so to speak. And my computer is very slow because I am just pushing this computer to its limit. And there is nothing else I could possibly shut down. So I don't know that I'm going to be able to show this because of how slow I am. I'm gonna shut my Facebook down on this one. Oh no, stay on page. I can't. Whoops! Almost shut my Facebook stream down. Sorry about that, guys. Anyway, I'm not going to be able to show that one, so it's taking too much time. I'll let it sit there in the background, and if it finally wakes up, I will let that happen. All right, so let's take a look real quick on our circuit breaker technologies. Zone selective interlocking is one of the options in 240.87 that will permit me to use arc reduction technology. But you got to remember, just like differential and others, it only protects you when the fault occurs in the zone of protection. So a fault that passes through everything, they go by as if they were programmed. So all of those devices will basically, you're outside of the zone, you basically, both devices go as they were programmed. And if you didn't program them, they'll probably cascade or whatnot. You won't have any coordination or anything like that. But you're not actuating it based upon an arcing event inside the zone of protection. The only time that the arc reduction is the zone selective interlocking works, and any of these other like differential relaying or arc quenching or any of those active arc flash mitigation systems is when the fault occurs in between the zone of protection. That is a very important piece of the pie to remember. All right. All right, so what I'm going to do now, since we are coming up at the end of that hour, I am going to, as I look through the questions, I'm going to bring up my, oh boy, I got to bring up my, all right, I am going to sign off, everybody. Thank you very much. Thanks for hanging in there. Thanks for all the YouTubers out there, and for all the chat sessions and whatnot. I'm going to cue up the outro. Take care, stay safe, God bless, and stay healthy. And hopefully we'll see you in, not next week, but the week after. So take care. I'm going to cue up the outro. And thanks to everybody who are still on